The next sorting algorithm we'll take a look at is called selection sort. With selection sort, we actually improve on bubble sort because we can cut down the number of swaps from O of n squared to O of n. That's the good news. The bad news is we still have O of n squared comparisons, so this is still an O of n squared time algorithm. The idea with selection sort is we're going to search through the entire array to find the smallest value. Once we found the smallest value, we're going to swap it with whatever value is at A0. So that means at this point, the smallest value is now an A0. We'll then repeat this process. We'll search the rest of the array, except now we're going to start at A1 because we don't need to search A0 anymore. And from A1 onward, we're going to find the next smallest value, and we're going to swap it with the value that's at A1. And we'll keep repeating this. So we'll start at A2, search for the next smallest value, swap with A2, and so forth. So we keep repeating this until we get to the end of the array. At this point, the entire array is sorted. Let's do the same example from before, except now we're going to use selection sort instead of bubble sort. We search the array to find the smallest value, which is 8, and we find that at A1. This means we swap 8 with the value at position 0. So we're going to swap the 8 and the 34. So now 8 is stored in A0. We'll now search the array again for the next smallest value, and we start at A1. Here we find that the minimum value is 21, which is at A5. This means we're going to swap 21 with the value at A1. So we're going to swap 21 and 34 in this case. We'll then search the array starting at A2 to find the next smallest value. In this case, it's 32 at A4. So we'll swap 32 with the value at A2. So in this case, we're going to swap 32 with 64. We'll then search the array again to find the next smallest value. So we're going to start at A3. We search the remainder of the array. We find that 34 is the smallest value, and that's at position A5. We'll then swap 34 with the value that's at position 3. So in this case, we're going to swap 34 with 51. We then do one more search. So we start at A4 and find the minimum value, which in this case is 51 at A5. We then swap 51 with the value at A4. In this case, that was 64. So we swap the 51 and 64. And now we have a sorted array. Here is our code for the selection sort algorithm. So we have our outer for loop, which takes care of both the number of iterations and also the starting point where we're trying to find the minimum value. So our first iteration, we're going to start at index 0. We're going to search the entire array to find the minimum value. The next iteration, we're going to start at index 1 and so forth. That's where we see this line, the int min equals I right here. Notice that we don't initialize min to 0, we initialize it to 1. That way we have a starting point to find the smallest value, because the body of this for loop is starting off by trying to find that minimum value. In fact, the for loop that's inside will search the remainder of the array, and when it's done, min is going to have the index that corresponds to the smallest element. Once we find that minimum value, we'll then do our swap. So notice that we do that in this section of code right here, where we're still using our temp variable for swapping, and we swap the element at index min, so a min, with the value at ai. So why is this O of n squared? Well, we are doing fewer swaps, but we still have the same number of comparisons. This is because we spend O of n time trying to find the minimum value of the array. The first iteration, we check all the elements. The second iteration, we check n-1 elements. Next iteration, we check n-2 elements, and so forth. So we still have all those comparisons like we did in bubble sort. And then we also have O of n iterations. So since we have O of n iterations, and each iteration takes O of n time, that means the total running time is O of n squared.